Welcome back to the course. The next unit we're going to cover is about the law of large numbers. All right, the law of large numbers. Oh, we can see the definition or what they say about this phrase. Right? The law of large numbers apply to a process for which the probability of an event A is probability of A, and the result of repeated trials are independent, right? So repeated trials, right? What it states that is if the process is repeated through many trials, the proportion of the trials in which event A occurs will be close to the true probability. The larger number of trials, the closer the proportion should be probability of A. Well, what it means is, well, as long as you do an experiment over and over, right, your proportion will yield to the probability. That's what you say. Right, so like we have seen before, the biased coin, right? If we flip it over and over, then the likelihood or the portion of head or tail you get will be how biased the coin actually is, right? That will be, like, in other words, the relative frequency approach, we're getting closer and closer to the classical approach. Right, so let's see in the example, right? The roulette. Roulette wheel has 38 numbers, 18 are black, 18 are red, and the number 0 and the 00 is green. Right, so that's 38 numbers in total. What is the probability of getting a red number on any spin, right? So you spin that just once. So the likelihood, right, you're getting a red for one spin, right? That is 18 are red out of those 38 spins, right? If you want, you could keep it in decimals. Right? That you could round it, may you record this number, 43768. 47368, okay. 47368. 42105. Right, and if you want to round it to 4 digits, 4737, right? To 4 digits, usually the probability. Okay. If second question, right? If a pattern in a casino spin the wheel 100,000 times, how many times you expect to get a red number? Right, so each time as we see the roll it over and over, the proportion will yield to the red, right? So intuitively, the number of red, that will be what? Number of times it rolls, multiplied by the likelihood for each row, right? Since the proportion will keep the same, so that likelihood each time will be that, and we roll large amount of time, so the product will be the number of red you get. In other words, this likelihood is proportion at this time. Right, so 100,000 multiplied by 4736842,105. Right, and we could round it, right? Keep 5 digits as a whole number, right? 5 figures as a whole number, then the remaining, we just take that out. 47,368. Right? If you want to put comma, you could, not necessary. Just leave it as a whole number there. Right? So that's this many times of red. This probability we found in part A will be just the proportion. Okay? Well, look like I'm not using the rounded digit since maybe it's not sufficient enough figures to multiply it 100,000, right? But I just use the one that is everything or as many possible. Okay, then expected value is when we consider two events, right? Which is on the value and the probability, then the expected value will be event one value times event one probability plus event two value times event two probability, and this can be extended to any larger number if you have multi-event and other probabilities, right? Including in this term in the sum. Like here, we just have one event. The expected amount of red number will be the event we have in total, that's 100,000, and the portion where it is red, right? Or the probability where it is red. So we see the example. Art auction to decide to bid 50,000 for a particular painting, right? Particular painting. You believe that you have a half probability, resell it client to New York for 70,000, and 1/4 probability resell the paint to the client in San Francisco for 80,000. Otherwise, you would have to keep the painting. Right? And what is the expected value of that 50,000 bid? Right. So first of all, we figure out what is the otherwise. Right, they say otherwise, what that means, right? You have 1/2 likelihood to resell it, you have 1/4 likelihood to resell it. So 1/4. So that has 3/4 of the likelihood to sell it, right? No matter the price. So what? The remaining 1/4 probability will be the likelihood that he just kept the painting himself, right? So that means here otherwise means 1/4. Right, so expect. Expect what? To pay 50,000 and nothing to sell, right? Just to have a bid 50,000 and sell nothing. That means he lose just 50,000. But in other word, another way that is what he just keep the painting, right? So that's something else. He sell it, or we use positive for net gain, right? Sell it a half likelihood to the client in New York for 70,000, but he pays 50,000 for the paints. Right, so that is the net cash flow, right? You'll see that in your chapter 4, right? That's net cash flow he have. And he has 1/4 likelihood, right? To sell the paint by 80,000, but still he has already paid the 50,000 for the painting. And he has 1/4 likelihood to gain the net cash of 3,000. I mean 30,000. Right, that's net cash of 20,000. And this one is net cash of 30,000. Right, so what? So we just use our calculator, right? Negative 50,000 times 104 plus 20,000 plus times 1/2. And the third one we get is 30,000 times another quarter, right? Another quarter. So at the end, that is 5,000. Right. So from the bid, he expects to gain 5,000. Even though he keep the painting, he lose $50,000 to buy it, but still he has the painting, right? He has the art piece that doesn't lead to the cash earning directly, but that is kind of property, right? That is kind of property. All right, the next question, New Jersey pick 3. Bet 50 cents and select a 3-digit number between 000 and 999. You get a winning number, you collect $275 and say the net. So net net gain will be $274.50. In other words, if you're not getting the single one winning number, you'll lose that money. Right? So if you play the game 100 times, what is your expected gain or lose? Right? So that is the question they can ask us. Right? So that's 000 to 999. That's will be 1,000 numbers. 1,000 numbers. And what? So if you want to build a table, winning or losing, that's 1,000 numbers and there is unwinning number. Not the probability yet. Okay. Win or lose, we get the money, right? To win, that's $274.50 of net gain. To lose is the person lose 50 cents, right? $0.5. And the likelihood to win that's 1 out of 1,000 number is the only one winning number, right? 1 out of 1,000. And of course, the remaining 909 numbers are the losing number. So 999.999 will be the losing one, right? So expected value maybe I could write it underneath. That will be a better place to do. Right, expected value is to win 274.5 by 0.001 and to lose 0.5 by 0.999, right? And then that's a single play, right? That's a single play. So we use calculator, 274.5 times 0.001 plus negative 0.5 times 0.999, right? That's negative 0.225. Or if you want to put in dollar sign in this case, that is losing 23 cents. Right. Then if you play it 100 times, that's law of large number. It's something else, but similar idea. Expected value is the money you expect to get once. And the 400 times is same proportion, so the expected value should also be 100 times of your expected value for once, right? That proportion already is ideal. So the multi amount of time go to law of large number, that's still the ideal idea, right? The ideal case. So that will be just losing 23 cents for the 100 game. So you expect to lose $23, right? You could use 22 to 5 to put that, right? So that will be $22.50. Either one is okay, right? Not that big off, right? Okay, so that is the expected value of our chapter here, right? And next unit will be on something else, right? So thank you.